When looking at ratios of areas compared to the ratios of the sides, and we're dealing with similar triangles, we know that if we have two similar triangles, in this case we have triangle ABC, which is similar to triangle DEF, we know that since they're similar triangles, that the corresponding sides in each triangle are proportional to each other. That means that if we're dealing with side lengths BC compared to EF, that ratio will give the same value as the ratio of AC compared to DF, which will give the same value as the ratio of AB compared to DE. Now in this lesson, what we're going to take a look at is the ratio of the areas of the two triangles and compare that to the ratio of the sides. Now, before we look at the ratio of the areas, what you do need to keep in mind is that we will rename the side lengths. Rather than calling it BC, remember that we can refer to that as side A, since it's across from angle A. Similarly, this will be side B, because it's across from angle B, and this would be side C, because it's across from angle C. And similarly in triangle DEF. So when replacing those values, rather than having BC over EF, you can take a look. BC would be side A, and EF would be side D. So we would represent that as a A over D ratio. And similarly for all of the other sides in both triangles. Now, the ratio of the areas of similar triangles is equal to the ratio of the squares of the corresponding sides. Now remember, we're talking about the ratio of the areas, and that's going to be equal to the value that we get when we take the ratio of the squares of the corresponding sides. Looks kind of like this. If we were to calculate the areas of both of those triangles and set up a ratio of those areas, identifying how much the rate is at which we either decrease or increase proportionally to get from one area to the next, that value would be the same as if we squared side A and took its ratio compared to the square of side D. And similarly with side B squared and its ratio over E squared, and side C squared and its ratio over side F squared. So the value of the ratio, again, not the actual area, but when you take the ratio of the areas, is going to be equal in value to the ratio of the squares. If you squared each of the sides accordingly, corresponding in each of the triangles, and perform their ratios, those values will all be equal.